Welcome to the Neuro Talk Evening. Today's topic is frequency filtering in broadband time domain for MEG and EEG signals, and today's guest is Andreas Widmann. And just to give you some brief introduction to who he as a person is, Andreas Widmann is a scientific lab manager and cognitive neuroscientist in the Eric Schrödinger's Cognitive and Biological Psychology Group at the University of Leipzig. His primary research interests are like auditory perception, attention, multimodal integration, and specifically the top-down modulation of early sensory processing by predictive information. And he's also involved in the developing and applying new analysis methods for EEG, ERPs, and pupillometry. And also, he has contributed to maintaining the filtering routines in EEG Lab, a program applied to MATLAB. And that's a research or programming language that is broadly used in the neuroscientific field and also specifically physics. And just to bridge to the topic or today's topic, all of us, or most of us, will at some point record MEG or EEG data. And once recorded, the real analysis of the data begins, right? But how should we filter our data and what is to look for in that situation? And that's where I would like to hand over to you, Andreas.
Okay, can you hear me? Good. Thank you for the kind introduction and for the invitation. I'm very happy to be here and tell you something about my ideas on filtering. So it's just, I will really focus. No, I have to share my desktop. I will really focus on the filtering step in the EEG or MEG analysis, which could also be, let's say, local field potentials or other related areas are very similar. And the point is, if you have some software like EEG Lab, you have a filter interface and you have to add some numbers, you have to make some selections. And the point will be to give you basically some guidelines. First, what happens there? So that will be the first part. Second, what for numbers or parameters to select. And if there's time, I will have a glimpse on the new approach on time frequency analysis parameters, which are very related to filtering in case you're interested in that. But if there's not sufficient time or more questions, this is also fine. If there are questions, just raise your hand, and I think Sebastian will then tell you how to proceed. So my talk, if I find it, is separated into three parts. First is filtering in the time and frequency domains. This is really experimental. I have never presented that in this way before. So please bear with me if it's too fast or whatever, just tell me. So this in some way goes to the heart of filtering. So but still I omitted that from previous talks because I felt it is too complex, but I think you are a smart and young audience and I think you will be able to follow me. But if you can follow me, you will get some idea really on the very basics, what the advantages and the possible problems are. And the second part will be pretty traditional, as announced, just what are filter responses, so how can we look at filters and what are the parameters you should enter into the fields. And in the third part, a relation of filtering and time frequency analysis. So in the first part, I would like to defend the following proposition. Most problems with spectral filtering or frequency filtering, I use that synonymous, arise from applying a frequency domain operation to broadband MEG or EEG time series signals. And there are three words in bold which need definition. So broadband is pretty simple to define. We can have a simple negative definition. Everything what is not a harmonic oscillation, so a sine or cosine wave, is broadband by nature. Second would be spectral filtering. What is that? And finally, frequency domain what is that? Spectral filtering means we want to attenuate or remove spectral power frequency components at certain frequencies of a time series while we want to retain others. And the purpose is very clear. We want to improve the signal-to-noise ratio of our signal. So we want to attenuate spectral power sorry, at frequencies which are dominated by noise and preserve spectral power at frequencies carrying our signal of interest. In the next frequency domain, it already becomes slightly more complex, but actually it's simple. It's a simply a different mathematical representation of our time series data. It's the very same data. It's just a mathematical transform, but it's the very same data. And we get from the time domain, so what you typically work with, your time series are the time domain data, and we get from time domain data to the frequency domain by Fourier transform. We have sampled data, so it's in fact the discrete Fourier transform. And for example, maybe you have all looked at MATLAB or R or something like that previously. And if you have a very simple time series, just zeros followed by ones, the almost most simple time series, we have in MATLAB the FFT, so that's just the implementation of the DFT, discrete Fourier transform. And we put in there 10 numbers, and we get back 10 numbers. Actually, if you count correctly, these are 20 numbers. These are 10 pairs of numbers, which are complex numbers. There's always one without, in each pair, one without I and one with I. And these are so-called complex numbers. We get 10 complex numbers from 10 samples in the time domain. And we get one number for each frequency component. What that is, we will look into a second. First, I would like to explain a little bit what a complex number is. That's actually nothing is complex about complex numbers. It's just a composition of two numbers. And you can understand that as two vectors. It just is there to mark a point in a two-dimensional coordinate system. So this is the first number, the so-called real, and this the second number, the imaginary component, which has an I because to mark it's imaginary. And these two numbers together, we can make just a very simple vector sum, give then the magnitude, or if squared, the power of the frequency component, and the rotation of that vector, which is, so this is basically the sum, so the absolute amplitude, and this is the rotation of the vector, the relative contribution of both parts. It's really the division of both, the ratio is the rotation of that vector. So these are the two numbers we need in the frequency domain. So we need the magnitude and the phase. Okay, then we change software. I prepared I prepared a Shiny app to basically interactively work with time domain data to the frequency domain. You can, at least you could in parallel work on that, but you could do also later. You will get all slides, and this is published. I might be better if you now focus on what I tell you and play around later, but you could do that also now. And there also the complete code is available from my GitHub page. So I hope I get that set up. So if you download the app.r and install the necessary packages, it's very simple to just run that app. Slightly bigger. So can everybody see that well? Is it too small? Okay.
Yes, perfect.
Thank you. So we have three inputs. First is the sampling frequency, which is arbitrary, doesn't matter. And then you have a input for the time series you want to analyze. It's again the step signal we had before, which is then displayed here in the top left. And to this third part, I will come in a second. So this is the time domain representation of our signal. It's just would be the input. And now this is the frequency domain representation. This is the output of the FFT. In orange, these were all the real numbers, and in light blue, these were the imaginary numbers. So we had I think a 0.5 for the first, and so on. So these are only the numbers we got from the FFT, no operation yet. And you see that we have a frequency axis. So the second number would be 10 hertz, depending on, of course, your sampling frequency you had as input here, up to 50 hertz. So with 100 hertz sampling frequency, the highest frequency you can represent is half that Nyquist frequency. And then we get in the second row the magnitude. This is just the vector sum of these two numbers. And the phase, we will not talk much about phase today, but just that is the relative amplitude of these two numbers. So, but what do these numbers mean? So that could be interpreted as the amplitude of the DC, so 0 hertz component, or the amplitude of the 10 hertz component in that signal, but there are no oscillations here. So what does that mean? So maybe in some of your courses, you heard that the Fourier transform decomposes your signal into a set of cosine and sine waves. And that is a bit hard to imagine, but what this means, this is really literal. So really we can compute a set of cosine and sine waves, which if added up together, results back in your time domain signal, literally. And that is exactly what we now do. So that is the 0 hertz DC component. Okay, 0 hertz is no oscillation, it's just a shift. But then we have the 10 hertz oscillation. So we have 10 hertz of oscillation of exactly the same length. So this is the same length as our time domain data. And we have a cosine component and the sine component here with a negative number. Then we have no oscillation in the 20 hertz and an intermediate amplitude in the 30 hertz, and again, no in the 40 and a small in the 50 hertz component. And really literally, if we add up all these 10 curves, we end up back into that time domain signal. Hard to believe, but it's really true. You can look at the code. There is absolutely no trick. It's really absolute simple addition. No cheating, nothing. And the idea of filtering is now putting in the frequency domain a weight on each of that frequency components. So we additionally have a weight vector, which typically is either 1, so we do not change the amplitude of that frequency component, or it is 0, because we want to remove the noise parts, which completely attenuates that frequency component. So we can now put different signals in time domain signals into that input data here. So let's start with that one. And the appropriately long weight vector. Okay, so that signal is, what would you guess? It's noise, isn't it? Is it noise? Okay, we will see. We filter it. So we just put successively zeros at particular frequency components. Now you see at the highest frequency component, again, 50 hertz, we have just a flat line. And there is a small difference between input data and output data, but not really noticeable. So we remove one more frequency component. Okay, still not really optimal, so let's remove even more. Okay, still looks like noise. And okay, even if removing until 35 hertz looks like noise. Okay, so if we remove everything above 30 hertz, up of 30 hertz and above, there might be something. So let's do it a little bit more. Okay, there a signal is appearing. So we can do even one more. Of course, that was, let's say, a bit prepared. So I added a wave, a Gaussian wave together with noise, and then I filtered the noise. So I've put the frequency components from 20 to 50 hertz to 0. I have removed them. And this is, we just have the remaining parts would then be 0 to 15 hertz. And adding them back together ends in that signal. So this is the good part of filtering. So we can remove noise components by attenuating them, multiplying it by 0 in the frequency domain. That is really how filtering works. And recover our signal. You see that the magnitude response of in the range of where our weights are 0 is then, of course, also 0. That's not the case for the phase response, but that's mainly due to rounding errors. So you should not be bothered by that moment. So the good part, we can recover signals if signal and noise bands are separate to some extent. But of course, there's always also a dark side. So I would like to go back to our step signal. No, wrong. And the respective weight vector. Again, only once. So we have a step signal. That's a test signal we use very often because you can demonstrate prototypical effects of filters on that pretty nicely. And that is because we have energy or power at almost all frequency components. So of the higher ones, every second is 0, but that doesn't matter. So it's a broadband signal. And the frequency domain has absolutely nothing to do with the process generating that time domain signal in any way. So when generating that signal, just imagine a light switch. There was no power before, then we take a switch and it's switched on. There's no oscillation in any way related to that switching on the light before or after or any time. So this is just a mathematical representation that has nothing to do with the generating process. That's really important that you keep that in mind. But that's what we use for our computations. And that's just how the signal looks in the frequency domain. And we have to be aware of the consequences if tampering with that thing in the frequency domain. So you can now imagine what happens if we add a 0 to the highest frequency component. What will happen? Any idea? You don't have to respond. You just should think a second about it. Maybe you can predict if we add a 0 here. We have a 0 here. And now we have in the filter output an oscillation, which is not there in the input in any way. That is, so this part is a constituent part in the frequency domain of that broadband signal. It's simply there. It's even if it's in the time domain, not related with generating, in the frequency domain, it's there. We need it to represent that signal in the frequency domain. And if we remove it, that has consequences in the time domain, possibly. And if we have a noisy signal, it's sometimes hard to detect this kind of artifacts. And one approach I frequently recommend if some people ask me how to recognize filter distortions or filter artifacts is to look at the difference between the raw and the filtered data to just see what we have filtered away. Because what we have, if there is any structure in what we have filtered away, not something which is not noise, then we have removed parts of our signal because we only want to remove noise components. So before, in the example before, we had only noise here, so we could perfectly recover our signal. But if there's structure, you have band limited your signal. So your signal was extended in the frequency domain across several frequency components, and you tempered or reduced some of them, which were important to represent your signal in the time domain. So, and that is the bad part or dark side of filtering. So you should be aware that if you have a broadband signal, even if no oscillation or anything oscillation like is in the generation of the signal, it's there in the frequency domain. So let's look at the little bit more plausible signal, which is the Gaussian we had before without any noise, to have that slightly clearer. So, and suitable weights vector. So we have just a Gaussian shape. And what you see now is that we have energy or power mainly in the low frequency components and no energy in the high frequency components. So that is the model we typically have underlying if we want to separate signal from noise. So we have frequency bands where our signal is not. So, and we can safely put them to zero in the frequency domain. So there's no difference in the, so we basically nothing we have removed. So we have oversampled our signal. So we wouldn't need that frequency components. And we can do that for quite some time up to some point where we indeed now get very small oscillations also for that kind of Gaussian shape. So that part of the signal is relevant for the signal. So we could possibly live with that small things here. But if we remove one more, it becomes quite stronger. And if you have even an additional one, now you have quite some severe distortion. So that is what you remove from your signal. This is the very prototypical low-pass distortion of monopolar signals, what ERP and ERFs typically are. So typically that are not ERPs are not oscillations, but monopolar signals looking a bit like a Gaussian, even if that is just might be random. And we can also, of course, approach that from the other side. No, that was the wrong. From the low part side, the lowest frequency component is always DC, so just the mean value of the signal. So we can typically safely remove that. It's just demeaning the signal. So the mean is now 0 is now here. So we have just shifted the signal. But already the lowest frequency component, so the 5 Hertz component here, removing that has really dramatic effects on the signal. That's why in ERP and so EEG, MEG, high-pass filters are much more problematic than low-pass filters because you have these kind of monopolar signals which are not oscillating. And if you remove these kind of low-frequency components here, this has typically dramatic effects. So you might have seen that if you have filtered EEG or MEG blinks, and you have put a high pass filter there, then these blinks look like that kind of Mexican hat. So this is the prototypical high pass distortion you see. It's pretty difficult to make a distinction between a distortion and an artifact in filtering, because just a distortion is something which is just the effect of the filter you would accept because you need the filter. The artifact is something you would basically, it's an unintended side effect, but the distinction is pretty tricky. So there's no clear-cut point there, which is what. Good. So that was the first part. I would like to quickly summarize. So just this is only for you if you want to play around with that at home. The take-home message of this first part is that you should know your signal of interest in the frequency domain to understand and avoid these undesirable side effects we had just seen. So even if no oscillations or nothing looking like an oscillation is in your time domain signal, in the frequency domain, it's there. And if you remove it, you will get problems. But it's a wonderful tool. It's just like, so the first example with the Gaussian in noise, that's really, I love that example because it's really, it's demonstrates the power in an incredible way. It's like magic, but it's just math. So you should try to avoid band limiting your signal. And that is basically the most important take-home message. Try to look at the signal you have filtered away. It transports relevant information, and it's a very simple operation. You just filter the signal, you filter it away. You can do that with earpiece, you can do that with ERFs, you can do that with raw data, continuous data. Very simple. It's just subtracting the input and the output, and the difference might be very informative. Good. So so you sent some questions. I have put them all together at the end of the second part, but I'm pretty sure there are some spontaneous questions already here, and I would have time for that.
So I would like to start. Especially if you're referring to one of the questions that has been sent to you prior to this talk, you've really shown the power of filtering, right? And what do you say? Isn't it also a risk that we really create something like artificial data? Because, like you mentioned, you can represent it and shift for filtering, and this not only will be misused with a certain purpose to like create data that seems like a signal or seems like a hypothesis conform. But also, I do think that filtering often is not really questioned enough, especially if you look at also things like ICCs.
You mean spatial filtering?
Yeah.
Yeah. So I wholeheartedly agree that that you should be aware of what you do if you filter your data. And indeed, I would say that in certain parts of the literature, there are effects which are introduced um, by filtering. I will have an example in the second part, and there's a bunch of literature on, in particular, high pass problems. Low passes problems are relatively rare. So low pass filters are typically not needed. So they are only used for cosmetic purposes. And I'm absolutely against using anything for cosmetic purposes. So if data are ugly, then they are ugly. These are data. So we do not want to hide that EEG and MET data are noisy. That's the nature of the signal. And so if this is only hiding, so for example, in ERPs and ERFs, we use time window means. So that is a low pass filter already. And for the statistics, the additional low pass filter makes absolutely zero effect. And just using that for the plots that they look nicer, that's not necessary. And for the high pass part, it's pretty, that can have absolutely massive effects indeed. For the low pass, I'm typically not so concerned if it's not too low. So we will have one example in the second part where it was really too low. And it also depends. So also in the time frequency analyses, these are filters. These are very narrow band filters. And only looking at a single frequency component in the frequency domain, more or less. And how you interpret the signal. So you have now seen that in each time domain signal, except on harmonic oscillations, we have oscillating frequency components in the frequency domain. So looking just at them with time frequency analysis, what do we really look at? Do we look at a process which is a generating process in the time domain, or is this a part of what we introduced by transforming that to the frequency domain? And that is always basically a kind of a way to go is understanding your signal. Does that answer the question a bit?
Yeah, I mean, it's way too complex to, or there is no real answer to it, but I really wanted to hear your opinion on that. And there's also a second question from Barin.
Yes, thank you. I'm sorry, I'm having a problem with my camera. Maybe it's a bit of a redundant question, but you talked about being cautious when using high pass filtering, and I've tried using that for some noise that is also at lower frequencies that sometimes for example, I did some signal processing on electrocardiography, and this noise kind of disrupted the detection of some important points, and so the algorithms wouldn't detect them well. So I have tried using I think high pass filters in that instance, and my question would be how can we filter the noise that it's at lower frequencies without filtering important parts out of our signal? I don't know if it's too specific or.
No, it's just it's absolutely not too specific. We have an example in the second part. In general, there is no general answer. That's the again, unfortunately. So it really depends what you need from your signal in the time domain. What you could do. So how your signal looks in the frequency domain. So what constituents are there? And also sometimes there are alternatives like demeaning, detrending, which can be used much more safely. Even detrending as in field trip with more complex, quadratic or other trends, which are problematic to describe in terms in math, in filtering math, because they are in fact leaky filters. But typically I try to it's always basically you have to apply common sense. Basically, if you we have an example where you change the properties of your dependent variable by high pass filtering, but if you have like breathing or other kinds of sorts of noise which you have to remove to look at your signal, you have to do that. It's
Right.
just that you have to be aware that I will show you. So also in that case, I would really recommend to look at the signal which you removed and check whether this possibly changes your dependent variable.
Okay.
So it's in the time range of your dependent variable, or whether it changes its amplitude, or whether it only removes noise.
Right. Okay, thank you so much.
Good. So then I will continue with the second part, which is a bit more formal. If I'm too fast, just interrupt me, please. So I will talk about filter responsive and filter parameters. I was using the word. And we'll start with some definitions. The magnitude response you already know. That is the weights we had in our previous example. So we have ones in the frequency domain for some frequencies and zeros for other frequencies. So that is that is the magnitude response of our filters in the frequency domain. And there we have a pass band, that is where we have the ones, and we have a stop band. This is where we have the zeros in our magnitude response. And separating these two is the cutoff frequency. That is the most important word of today, which separates pass band and stop band. And we can do an inverse Fourier transform. This is just math. It's not even complex math. Basically, you can follow that in very simple terms. And the inverse Fourier transform gives us a time domain signal. And as the filtering in the frequency domain, as we did it before, typically is problematic just because the signal is far too long and the FFT would simply take too long. We implement typically the filtering actually in the time domain. So what would be multiplication here is mathematically perfectly identical to convolution here. If you have not heard about convolution, don't worry. It's just multiply, add step in steps. It's nothing complex. And you do not have to do that manually. You just have to understand that this is the impulse response of a filter in the time domain, which are your filter coefficients. And a very important aspect of your filter coefficients is the filter length, which is just very simple, the number of filter coefficients. And we have the filter order, which is even more relevant. This is just the length minus 1. It's just the number of dots here minus 1. And typically, it's pretty complex to design filters in the frequency domain. We have much better tools to design filters in the time domain and do just the Fourier transform to see their magnitude response in the frequency domain. So what will happen if we filter what will be attenuated and what will not be attenuated? It's just easier because just in the Fourier domain you have the complex numbers and you have to always look at both sides, but that's relatively trivial. In fact, it's perfectly irrelevant, really perfectly irrelevant whether we do that in the time or in the frequency domain. And these filter coefficients are at the same time the filter output if I would filter an impulse, which is just a 1 around lots of zeros. That's why we have the impulse response. These are the filter coefficients, and at the same time, the output of filtering the impulse. Much more interesting than the impulse is the step response you also had seen in our example before, because that is just a perfect test signal where we can see effects of our filters on time domain data. It's a very extreme signal, but it's good to show the effects. So this is then the step signal filter output, so the step response of our filter. That's the filter output if filtering a step with our filter. And this is the very prototypical low-pass filter artifact, just we get smoothing of our sharp gradients. If we filter away the high frequencies, the signal will be smooth. Good, so you know everything essential about filter responses, so we can get to the filter parameters, which you can manipulate, which are 5. Most of them are absolutely trivial. You will understand them immediately, but just for the sake of a formal treatment, I will add all of them. So first is the filter type. We have a low-pass filter. We let low frequency pass and reduce high frequencies, or vice versa. The high-pass filter, we let high frequencies pass and attenuate the low frequencies. Of course, we can combine both types. Then we get a band pass filter, and here we have the pass band. So we attenuate high and low frequencies, and we can invert that and have a band stop filter, attenuating only particular frequencies and let lower and higher frequencies pass. I would like to switch back for a second. This is the step response of a high-pass filter. This is the prototypical high-pass filter artifact, the slow return to baseline. That, for example, happens if you would filter across a discontinuity, what you never should. So do not filter across signal discontinuities. But if you have a sharp signal in your some sharp effect in your input signal, the slow return to baseline is the prototypical high-pass filter artifact. The bandpass, of course, combines both types of artifacts, and band-stop filters have very strange artifacts. And in fact, because of this kind of problems, I do explicitly recommend using band-stop filters only if you absolutely have to. And also do not use bandpass filters for a reason I will explain in a second. I will come back to that. So that was filter type, what first filter parameter. And the absolutely most important filter parameter is the cutoff frequency. We had already defined that, separating passband from stopband. And we can have a very clear rationale for how to select that. The signal should be completely in the passband. You already know why. You should not band limit the signal and remove as much noise as possible. So should be as close to the signal as possible, but not band limit your signal. So that's our different low pass filters, the step responses of different low pass filters. And you see the more high frequencies you remove, so the reddish color keeps the sharpest and removes the smallest amount of high frequencies. And the more high frequencies I remove, the more shallow the step becomes in the time domain in the filter output. And almost similar for the high frequency part, just the other way around. The more high frequency I remove, the more flat the signal will get, but you will also have this kind of filter ringing artifacts here. And you already know where this comes from. So I think that was why I introduced the first part, because it's really hard to explain where this filter ringing type comes from. That is really because you removed parts of your essential parts of your signal. Typically, the rationale for high-pass filters for ERPs is very clear. These should be pretty low, but there are, of course, always exceptions. For example, if you prepare ICA data, it's now recommended with 1 Hz high-pass filters, or in ECG, you will have very different filters. That is pretty application dependent. So the third relevant filter parameter is the so-called transition bandwidth or roll-off. I cheated a bit on 3 occasions. This is the first one. We can actually never have a rectangular step in the frequency domain. That is impossible. You will need an infinite length time domain signal. So I cheated a bit. But actually, we always have a transition between the passband and we need to have a transition between the passband and the stopband. And but we can control how steep this transition is. The part where the passband ends, so we have a deviation from the from once, or a deviation from 0 in the stopband. That is the transition band, and the cutoff for FIR filters, what you basically in EEG, MEG hopefully exclusively use. It's always in the center of the transition band at half amplitude. So where we attenuate the signal by 50%, or minus 6 dB in logarithmic units. 50% is minus 6 dB. For IIR filters, infinite impulse response, sometimes also minus 3 dB, so 70% amplitude is given as the cutoff frequency. But some other aspect, you should always, if you report your filters in papers or read papers, you should always check, did they report what kind of cutoff they report. So you should always report minus 6 dB or 50% cutoff. So that is the actual pass band, and that is the actual stop band. With one exception, in EEG lab, they want to have a different definition of cutoff frequency in one of their filters. You just have to know that if you work with EEG lab, there the cutoff is the edge of the pass band. For reasons I do not want to explain, I do not want to defend that because it was not my idea to do that. It's it has traditional, it's traditional form. So we can have differently sharp transition bands or roll-offs. And now the key is the longer the filter, the sharper the roll-off. Or the shorter the filter, the more shallow the roll-off. So all these three filters basically have a relatively similar step response, but you see that the red filter basically ends here and here. It has only 9 points. So that was the length of coefficients here. So what is the good part is that we have these kind of artifacts, you know where they come from. This is filter ringing, so this deviation here or the deviation here. They can distribute that in the time domain only on a much shorter region because they are shorter. So the rationale for selecting how short the roll-off should be is always the filter should be as short as possible or the roll-off as shallow or smooth as possible. That you have your artifacts restricted in the time domain. So that's really filter ringing is we remove the frequency components. And now what the extent here is now the length of your FFT. And if this is short, then you will only distribute this removed frequency over a very short section of your time domain signal. So use as shallow as possible filters. I already explained ringing. Low pass should not be too sharp. For the high pass, it's a bit different. So we typically have signals which have very low frequency components. So our low pass cutoffs have to be at very low frequencies. And necessarily, of course, then we need very steep filters for that. Nothing you could do against that. But this is the reason why you should not use bandpass filters, because in all packages, MNE, whatever, the roll-off of the high pass and low pass part of a bandpass filters always have exactly the same roll-off. But that is actually not necessary. If you need a sharp roll-off for the high pass part, but you could possibly use a very shallow roll-off for the low pass part. And if you separate them and just use two filters separately in serial order, and the order doesn't matter, it's perfectly irrelevant, it's all linear, you could have the low pass artifacts very restricted in time. For the high pass, you are lost. But that's the reason not using bandpass filters. Use high pass and low pass filters separately and tune them separately to your application. I told you I will cheat 3 times. This is the second time. Actually, the magnitude response can not only be not rectangular, but it's also not perfectly flat with finite time domain signals. We have some kind of deviations from our expected response. This would be pass band ripple, and this would be stop band ripple. And the ripple is just the deviation from the expected frequency domain. It was correct. The deviation from the expected frequency domain amplitude, 1s here or 0s here. So that means that this deviation is also termed and more relevant as attenuation, because we want to have a 0, and if we do not have a 0 but a higher number than 0, we have a reduced attenuation. So the signal is not fully suppressed here. And this was also the unfolded magnitude response. Actually, magnitude can only be positive. We cannot have negative parts here. I only had that representation that you know where that bumps come from. Actually, this are negative parts where we have an inverted phase response. And we can control the attenuation by so-called windowing. This is available just in the software packages. You do not have to know much about that. You just look what attenuation I want to have, for example, 54 dB, and then you can select which window type I have to use for that. More attenuation or also less passband ripple means also longer filters. So besides roll-off, also the amount of attenuation, so how much we attenuate the signal in the stopband, makes filters longer. Typical default would be minus 54 dB, which would be 500 times attenuation. Minus 60 dB would be 1000 times attenuation. That's why we also typically look at the magnitude response in logarithmic units, because this stopband ripple we couldn't see actually in the linearly scaled magnitude response. The ripple is so small. So it would be here is factor 1000. It would be impossible to see that. But here you can see basically that this filter has minus 54 dB. And we can have that. We could do that almost infinitely by different window types. And this in the passband, that means that we have a deviation of 0.2%, so 2 per mil, which is really good already. So even short and reasonable Hamming window filters, which are most common, are pretty good. And third time I cheated, but promised last time. So we had we cannot only have not rectangular roll off, and we have passband and stopband ripple. Necessarily, each and every filter, necessarily without any exception, has a delay. So if we filter, the output signal is by some amount delayed relative to the input signal. And this is, of course, bad. This is bad, whatever. It's a constant. You cannot do anything against that. And to describe the delay in the frequency domain, we need the so-called phase response. I showed you in the first part what that is. That is basically simply if this line is rotated, then this frequency component is delayed, and the more cycles I have, so the more. Good part is if we have a line here, in that part, if we have that means we have a linear filter, we can correct for that delay. In FIR filters, in most implementations, all these filters are linear phase. And so they have a line here. That means in the time domain, the impulse response is symmetric. And then we can correct that just by shifting the time axis, basically, and make the filter zero phase. So 95% of filters you see are zero phase filters. But there is a drawback of correcting the delay of the filter, is that we introduce a kind of non-causality. So we have, this was the input signal, the step. So in the output, the signal already deviates slightly before the step occurred in the input. So we have non-causality. So we have an effect before the signal even changed. That might be a problem for particular applications, so be aware of that. So there was a big debate some years ago. I would consider this effect as typically natural for high-pass filters. For low-pass filters, due to this very low return to baseline in both directions, these problems are much larger than this kind of problems here. This is only 1, 2, 3 samples. But for high-pass filters, this is a serious problem. So it depends how whether in your particular application causality is really depends really on the scientific question you ask, whether that is a problem or not. You should just be aware of. The problem is that there is not really a good alternative. So we have also nonlinear phase filters, which have smaller delays. The line here is unfortunately now not linear, so nonlinear filters. That unfortunately means that different frequency components have different delays, and that distorts the shape of our signal in the time domain. It's really a distortion. It's partly, we have an example in a second. It's basically partly hardly recognizable. The delay still isn't zero, but it's smaller. For low pass filters, this is typically not an option. There's also the problem is not so big. For high pass filters, this is different. High pass filters have this very long non-causal effect. So this is even a good example. And nonlinear, non-causal high pass filters have very small delays and in the pass band typically relatively linear. So we can use them sometimes if causality is an important issue. So we do not want to use non-corrected linear phase filters. They have huge delays and it's like a scale. You know the delay and you would immediately subtract it. It's just like you have a scale which shows 100 grams and you put 10 gram extra, it shows 110 grams. You will know it's what you put on there is 10 grams. That's the very same thing here. So even if you would not correct for the delay, you know it's there and you would mentally correct for it. And so it's not an option. So typically we use zero phase filters and sometimes we use nonlinear phase causal filters. So some examples from the ERP world where I come from. This is an ERP experiment with oddball experiment with mismatch negativity, with standard stimuli and deviant stimuli. These are the raw unfiltered data. Actually, we would not need filtering here as the data look nice, but I need an example. We have a P1 and N1. We have a N1 and mismatch negativity also for deviance, and N2 and a P3 because they were to be detected. Now we want to filter that data. They were actually filtered on the continuous data. You should typically not filter epoch data. So first, a low pass, which looks quite reasonable. The signal does not look really distorted. But let's, to be sure, look at the difference of deviant raw minus filtered. So what I recommended you to do. And indeed, for the deviance, there is only noise. We have only filtered away noise with our 15 Hz low pass filter. For the standards, that's somewhat different. There is something relevant. We have removed our P1 response, which is pretty high frequent. So this is higher than 15 Hertz, and we have removed it. So there's structure in the raw minus filtered output, and this way you can detect distortions you introduced into your data. If you use a much lower cutoff, low pass filter, 7.5 Hertz, you see that we have now dramatically, beyond any doubt, distorted the signal. You have this kind of very clear rhythmic structure, which it comes from. And of course, the P1, N1 effects in the standard are even stronger. For high pass, that's slightly different. The high pass of 0.7, which is already high, but for demonstration purposes, I needed, so 0.1 didn't affect the signal here. So this is already this slightly distorts our standard, but it's at least almost linear. For the deviance, that's very different. So we have a very large, very low frequency response, and we see in the raw minus filtered the frequency components we removed. Oops. And what we now do is, this is also non-causal. So by removing these P3 parts, we have enhanced the amplitudes of our N1 and N2 responses. So that's really distortion. But you can see that you change the signal in that time range by your filter. That's why this raw minus filter is so valuable. And of course, this is much more emphasized with the 1.5 hertz high pass filter, which is now really something you should never use in the ERP world. The alternative, of course, this does not only shape the time series data, but also that's also visible in the topographies. Actually, it changes the topographies. I told you to possibly, for high-pass filters, use a non-causal minimum phase filter. And indeed, these non-causal effects are now gone. We have even a slight reduction of N1 and N2. But now the P3 is completely, I don't even have a word for this. So it's really completely misshaped, distorted. It has nothing to do any longer with the input signal. And so you also see here in the different that this is pretty problematic, these non-linearities. So let's have a quick look. So we had 5 filter parameters you can adjust: filter type. That's now filter type, cutoff, roll off or transition bandwidth, attenuation, and delay. And we started from how that we wanted to know what to input in, for example, EEG lab. So I would like to have a look at 2 EEG lab filters. First, this is the default filter. Here we can input a lower edge of the pass band, what is now their cutoff, and the higher edge of the cutoff. So this would actually be high pass, and this would be the low pass. So the naming is pretty confusing, in my opinion. Anyway, you can put a number in only one of the boxes, then you have a high pass or a low pass filter. You can put the filter order, so number of coefficients -1. Default is automatic. That is a problem. You should not use anything automatic. So there is that is what I could have. That was basically the compromise, to have a manual definition is recommended. You can read how this in the documentation how this default works. It's just for high pass. It's complex. You should read it. I can now report it, but it's a pretty complex heuristic. I recommend really thinking about it and using a different interface. Sorry. You can invert that, so to have a notch filter instead of a passband filter, and you can have a minimum phase causal nonlinear filter. It's no longer better. I have to remove that. You can plot your frequency responses. That is basically the MATLAB here, the MATLAB version of what I showed you. This is for high pass filters only. That is only about the implementation. The output will be identical within limits of numerical precision. So you have floating points, so there are rounding errors, but that's the only difference. So this is time domain and frequency domain filtering. Depending, nowadays frequency domain filtering is faster. 10 years ago, it wasn't, but now with new graphics cards and everything, frequency domain filtering can even be FFT-based filtering, can even be sometimes faster, but that is only about speed. I would recommend, if you use EEG Lab, to use the window sync filter. So the math behind is exactly the same. Also, the default filter is based on window sync. So that is the math are identical, but here you have control over each and every of the 5 parameters. So you have cutoff frequencies, 1 or 2, whether it's high pass or low pass, or 2 in case of band pass or band stop. You can select then the filter type. Then you can select the window type. It gives you the attenuation. For Kaiser is a window type you can additionally tune to basically infinite attenuation, but then of course filter coefficients will also be almost infinitely long. Key point is now that we can, from our, let's put a 40 here, a 40 Hertz low pass filter. No, I wanted to have 48. You should think how the filter order defines the role of here. So, and we can estimate that. So we have math to do that. So you do not have to trust some EEG lab default heuristic. You can do that yourself. And let's say we have an EEG and we have 50 Hertz noise. You do not want to have a stop band, band stop filter. So we want to have at 50 Hertz our maximal attenuation. 48 is in the center of the transition band. So if we want to have maximal attenuation, we need a 4 Hertz transition band plus 2 to the left, plus 2 to the right. Then we have maximum attenuation at 50 Hertz. And now we can have, first we can select again our attenuation. It is transferred from the previous window. We have the sampling frequency, and now we enter the transition bandwidth, which is 4. And then you get a number that is the filter length, which was made by default in the other window. But now you could have basically the sharp roll of you wanted to have. So you wanted to have everything below 46. So let's look at the filter responses. Then we immediately see that. Oops. Now we see exactly what I showed you in all the previous slides. We have a magnitude response in linear terms. So 50 Hertz, we have full attenuation at 50, around 50. It doesn't work now. Sometimes it shows the numbers. At 48 Hertz, we have minus 60 dB or 50% amplitude. And here we have typically ones. We have an attenuation of around minus 54 dB. This is the impulse response and the step response. This is delay corrected. So we have a zero phase filter and we have a flat line in the pass band and transition band in the phase response. And also outside of in the stop band, this is basically all linear. This is just this noise here is just the ripples where we have, or basically in the unfolded magnitude response would be below or above the 0. So there's nothing special about that. And if you, that's basically, and of course you can have a delay corrected causal filter if you really want to use that. And frequency domain filtering, but that is the output is identical. So that was the EEG lab version. No, I made something wrong. The very same filters are available in Fieldtrip. I do not have an interface version because you just work with these kind of configs. We do not have to go through that. You get these slides. You can use them as reference later. The only difference, so you have for each parameter you just have a line. So it's we need only the type, which would be high pass and low pass by LP or high HP there. Oops. We have a delay correction, 1 pass or 1 pass 0 phase. There's also 2 pass, which you should not use with FIR filters. At least not with, no, you shouldn't. The only shortcut you can take, you do not have to press the estimate button to estimate the filter length. If you have a transition bandwidth, you can just put directly the transition bandwidth and it will compute by itself the necessary filter length. Everything else is basically the same. So take home message of the second part, adjust intentionally all your 5 filter parameters you have. So think about each of them and adjust them to your application and to your needs. Do not trust any defaults. Think about it and put them manually. Typically, shorter filters with a slower roll-off are to be preferred, but sometimes you need sharp filters. Avoid band stop and band pause filters. Use linear phase filters non-linear phase filters if you need them, but take care. And what I did not yet talk here is that sometimes people or software suggests to use two-pass filtering, so filtering forward and backwards to correct for the delay. That's only needed for asymmetric filters. And these can be easily replaced by symmetric filters. So you should not use that actually. Check the filter responses. So these 5 fields we just looked at, whether this really is what you asked for. A message from heart is, if you write papers, report all your 5 filter parameters for replicability. So the effects of choosing a different parameter can be dramatic. So you basically see already why. So for replicability, it's really essential. And also, if you read papers, check whether they are correctly reported. Annoy authors by asking. Never filter across signal discontinuities, ever. You shouldn't do that. So if you have epochs or otherwise blocks or press pause in between, you should filter the different parts separately, ever. And I cannot avoid but stating that you should also think about avoiding filtering by taking the appropriate measures beforehand. So each noise you do not even record, you do not ever have to filter out. So care about participant comfort and compliance so that they sit comfortably. You get less muscle artifacts. If they do not sweat, you have less low frequency artifacts. If they do not move, you have less movement artifacts. Check, for example, in EEG electrode impedances, avoid electromagnetic interference for both MEG, EEG if possible. And also trial numbers. So also averaging is a filter. It's a flat filter, but it avoids noise, which is uncorrelated. And there are also for parts, in particular high-pass filters, there are time domain-based alternatives, demeaning, detrending, even with more complex trends, so quadratic or other trends. And there are, for example, for line noise, there are EEG Lab plugins to remove line noise in the time domain. You just model your line noise and subtract it, so you do not filter it. So time for questions. How late is it? Okay. You sent some questions. Should I try to answer them first, or should we first? I think I would like to hear your questions first, but I'm open to any procedure.
First of all, thank you very much for a very interesting talk. Of course, if there are any questions from the audience by now, please feel free to ask them. Otherwise, I think we could continue with those questions, but I can ask one of the questions right off the bat because it's a question I would like to ask you. I know this is your talk today has been mostly about ERP, and therefore not that much regarding real oscillations if you use a steady state response, for example. But I had a very short talk with Professor Andersen that I've worked for in Denmark, and we've discussed about filtering, and then we basically agreed on not filtering at all using the steady state response, and I think that's a quite appropriate way, because until now it is quite hard to separate, or basically impossible from what I know, to separate a ongoing EEG oscillation for like alpha band from a stimulus-driven oscillation. Is there anything that you know that is currently being worked on to help with that kind of issue? Because I mean, I don't know how much, how if it makes a huge difference in terms of the data in the end, but it is something you could take care of, right?
For steady state is a filter. It's a very specific filter, but that is filtering. It follows exactly the same rules we had here. So you typically you use complex demodulation, but that doesn't the actual math doesn't matter. But in the end, you use what you have is a narrow band filter over your carrier frequency. I can show that mathematically. So that's it's only a narrow band filter, and then you either do the Hilbert transform or you use the sine and the cosine filter and add them up, basically. So Regan type. So you typically do not need any other filters for steady state responses. So it's already a filter, and you look at your signal of interest. You filter out everything else except your carrier frequency and some range around to change the amplitude modulation of your carrier frequency. You should be aware of that you should remove large artifacts, so blinks, whatever. But that's basically the only thing I would do for. It's indeed correct not to filter in the pre-processing of steady state responses. And if that was your question, I would. So I think that is then what you sent as a question, right? So this is basically one of the I don't know or what at least one of the in my opinion hot top 10 emerging topics in the field. Basically the differentiation of oscillations and aperiodic or basically background 1 over f EEG. But this is emerging, so there is nothing ready-made in any of the packages. But I think the most prominent toolbox is I don't know how to pronounce that. And I do not dare do that because if you want to put that on YouTube, but I do not know. FOOF, it's because it's F, so 1 over F toolbox. There's basically from Wojciech Group and also Bob Knight and others, very influential papers. They model that. They model 1 over F and the different parameters and changes in 1 over F and deviations from 1 over F, which then is basically oscillation. There's also a group emerging from the EEG lab, SCCN group. There's a link where they discuss any kind of these issues. And there's a very recent paper from Eric Rawls on basically oscillatory and aperiodic contributions and possibly how to parameterize them. But it's emerging, so I do not have a ready-made answer for that.
Thank you very much. I'm definitely gonna have a look into before I go back to finish the analysis. So, are there any other questions from the audience right now? There's one.
Yes. So at first, thank you for the interesting talk. It was pretty cool insights into MATLAB 2. I wanted to ask if you have any specific recommendations for filtering high frequency EEG data when the downstream goal is to do phase-based functional connectivity analysis. I know it's a really specific question, but maybe you have something in mind because you said that I was wondering if especially the effects of filtering on phase-based metrics could be a really important thing to keep to be aware of when choosing a filtering method.
So there was a debate some years ago. So if this is on YouTube, I have to take now very careful wording because there are some people very strict about that.
Okay.
So take my response, please, with a grain of salt. So any filtering will necessarily always affect phase. There's no way up, basically, around that in some way, except in the passband it should be. Of course, there are different points in the passband the phase shouldn't actually be changed, but it's a difference between instantaneous phase, so the instantaneous phase in the time domain, which is very different of the phase of the frequency components. So in QEEG, any kind of filtering, it's even if the slightest noise will change the instantaneous phase immediately. So the debate at that time was about whether removing ICA components changes phase, and yes, it does. And you remove noise, so it will affect the instantaneous phase. But if it's about, let's say, phase relations, so for example, phase-phase coupling in time frequency analysis, if it's in the pass band, it should be fine. There shouldn't be any major problems. So because just we have linear phase and linear phase properties, so the different frequency components are shifted by the same amount. So the same phase, so it's linear. But there might be special cases. But if you use it for pre-processing, if all your frequency components in the pass band, you're typically safe. But instantaneous phase will change.
Okay,
so if
thank
you do a
you.
Hilbert transform on the signal and compute the phase of the Hilbert, it will be different, always, necessarily.
Yeah, okay. That makes sense. Thank you.
So then I think
So then I will go through the questions you prepared. So are there computational methods to reduce the smearing in the frequency time domain? Basically, I hope you know the answer by now. You use short filters. Use the shortest filters possibly with the most shallow roll-off, and attenuation only as strong as possible. For frequency domain smearing, I'm not sure what frequency domain smearing refers to. Basically, it's about separating frequencies. You of course need a sharp filter, so a long filter in the frequency domain. So that's a trade-off. And the signal should be completely in the pass band, also in time and frequency domain perspective. Does that answer the question? Not sure whether the person is in the audience. There might be no general answer towards this question, but what do you suggest how to choose a filter without distorting signal timing? So which trade-off would you still consider appropriate? Typically 99% of EEG, MEG, well, 95 would be zero-phase filters, so delay correcting filters. And for everything where causality essentially matters, you have to use some kind of minimum phase filters. There's basically, you only have that two options. So it's unfortunately a yes/no response, more or less. So it's not really a trade-off. It's does causality matter? And so, for example, if you what is causality? If you, for example, look at pre-stimulus phase and check whether pre-stimulus phase is related to some post-stimulus feature and one amplitude, whatever, then causality matters, because if you filtered before and some feature of the N1 might non-causally be now transferred, it's a bit smeared, non-causally to the pre-stimulus phase, you have a problem with causality. So there's a paper about that, so for example, if you have these relations between different delays, for example, then causality matters, and then you should be careful. Hope that answers the question. Otherwise, just raise your hands, please. In terms of zero-phase filtering, aren't we creating irregular data with those methods? Yes, but please define irregular. What is irregular? It's, of course, the zero-phase introduces non-causality, but non-linear affects shape, so it's also irregular in some sense. So you have seen how on a P3, for example. That is not ERP specific. That affects basically everything. So non-linearity is has problems with everything. And delay by itself cannot be avoided. It's in the system. If you filter, you introduce delays you have to correct for. So with your back to your phase question, of course you should not use nonlinear filters for that. Otherwise you are doomed with phase analysis. Is there a possible procedure to minimize effects of filtering on statistical power? I would like to phrase I think it's a twofold response. Actually, we want to do the opposite. Filters are intended to improve signal-to-noise ratio, so maximize effects on statistical power. We want to enhance power. If we do not, we should not use filters. So we had the example that time window means make low-pass filters obsolete. I showed you that. So we should not use filters for cosmetic purposes. If they do not improve your data or your analysis, you should not use them. I think the question rather was for side effects or distortions of filtering, and I hope I told you the relevant strategies. Try to keep all your signal in the passband. Do not band limit your signal. And second, look at the difference between input and output, so the signal you have filtered away, because then you see whether you have a relevant change of your parameter in your dependent variable, for example, at the time point of interest or the feature of interest. And final question, at what frequency can we remove baseline drift without significantly attenuating and distorting the low frequency neural components we want to study? There is no general answer, sorry. That very much depends on the type, slope, frequency of that low frequency distortions, and also the frequency range of your signal of interest. I would really, what I typically do if I don't know anything beforehand, I use different filters, and I put really the filtered away signal one by each other and look which is possibly problematic or not. So which part reduces the parts I really want to remove. So is that noise? So I look, did I remove the drifts? So are they in the filtered away signal? And did I additionally remove relevant, significant parts of my signal of interest? And you all see that in the signal you filtered away. So this is informative. But sorry, there is no general answer to that. Oh, sorry, one more, but this was very specific and not related to spectral filtering. Sorry, not my generalized filter models, and ICCs are not my area of expertise. This would, even if I would be an expert, it would at least need additional 1.5 hours to dig into that. Sorry. And the final question was the one we have already answered. It's now basically like Monty Python would say is now for something completely different, but actually it's not so completely different. It's about a little bit about the relation of filtering and time frequency analysis, which is very closely related to your steady state part, because that's just one way of time frequency analysis. Question first, anybody has an idea what that is?
That's a wavelet.
That's a wavelet, great. Do you know which type of wavelet? Just guess. It's
A Morley
incorrect
wavelet?
answer. Pardon?
A Morley wavelet?
Exactly, that's the Morley wavelet. Morley wavelet is a cosine or sine wave multiplied by a Gaussian envelope, and we use them to convolute in the time domain our signal to time frequency narrowband basically a narrowband analysis. And this, sorry, can you still hear me? So
Yes.
somehow my something changed how my earphones transfer. This can be considered as an impulse response as a filter in the time domain. And if you do the Fourier transform and look at the magnitude response, you immediately see that this is a filter. So we remove low and high frequencies, and we have at the center frequency maximum. This is a filter, and time frequency analysis is nothing else but a set of filters we put on the same signal and put it together at the end. This wavelet has a 20 hertz center frequency, so we have a peak at 20 hertz in the frequency domain, and a whatever you would call that, its duration, I don't know, of 7 cycles. I'm not sure who of you has heard of cycles in the definition of wavelets. Okay, at least one person. Great, because all that is now about cycles, and that cycles, my proposition is that cycles is the next, so cycles is used in several software packages, and also you read it in publications a lot. And my proposition, I would like to defend that cycles is a maximally opaque intransparent unit for Morley type wavelet, and that there are much better alternatives. So that is what this third part will be about, finding a reasonable unit. So that would be 7 cycles. So in which way is that related to anything in my Morley wavelet? Actually, the resolution of a wavelet depends on the Gaussian shape we multiply with our frequency. And the Gaussian has 2 parameters, the mean, which is 0 in our case, and the standard deviation. So sigma t in the time domain, or sigma f in the frequency domain. And this is where these cycles actually come from. That's just a tradition. When Talon-Baudry and others first applied that to the EEG or MEG, that's how they defined their wavelets. That is the ratio of the spectral standard deviation divided by center frequency divided by 7 would be the standard deviation in the frequency domain. But there's absolutely nothing with cycles in the frequency domain. So this 7 is absolutely unrelated to cycles. If we transfer that definition to the time domain, the 7 cycles would indeed be 2 pi times the temporal standard deviation. But that is maximally intransparent. 2 pi something as a resolution of a wavelet. That's really completely inaccessible, in my opinion. But actually, that is a filter. And we have a point with -6 dB attenuation. What would be in filtering typically a cutoff frequency. And now, if we have the half amplitude, we have a parameter for Gaussians, which is called the full width at half max in the time domain or also the frequency domain. That is just the width of the Gaussian at half the amplitude in the time domain and in the frequency domain. And I would like to suggest that this is a reasonable parameter to describe the resolution of wavelets in the time domain and in the frequency domain, which is very accessible because it's the very same parameter you would use for filtering. This is actually not my idea. That was first suggested by Mike Cohn, but there's an implementation missing. So he described that, and there's also some code, but it's completely inaccessible. You cannot use it in software packages. And what I now forget that slide. What I now did is program a calculator, how to calculate the different units from and to cycles. So even if you read in the paper, they use 7 cycles, you can now use that calculator to compute the different units of spectral and temporal resolution. That is the MATLAB command line interface. So basically, you can just download that, and it's also part of EEG Lab, at least in the developer version. It will be also in the regular version of the next EEG Lab versions. I'm not sure about Field Trip. They have their own approach. If you use the function on the command line, you have inputs, so a frequency vector you would use as in time frequency analysis, let's say 10, 15 to 40 Hertz. We have a width parameter, which can now be anything. So here I would have a width unit of full width at half max in the time domain of 200 constant 250 milliseconds. So actually that would be an STFT, short-term Fourier transform or Gabor transform with a resolution of 250 milliseconds. And we need a sampling frequency, just we need it for the math. And that would be the number of cycles we need at these different frequencies to put into your software of interest. Or you can also do the other way around. You can have as a width unit cycles and put here the cycles parameter and the frequency and the sampling rate if you read them, for example, in a paper. And then you get a width table which reports all parameters. So we have first the frequency, second the cycles. That would be what you have put in there. Then we have the full width as half max in the frequency domain, so 3.5 Hertz constant in that example. It's in the documentation. The order of columns is in the documentation. You do not have to remember that. You just need to look at help TF cycle calc, and then you get the order of. Then the full width at half max in the time domain, 250 milliseconds. Then we have 2 sigma t. I should have, that is just a traditional unit. All the Talon-Baudry, Bertrand papers and all that community uses 2 sigma, which is very similar to our full width at half max. But I think at long term, the full width at half max will be the better unit because it's just very intuitively accessible. And then we have finally sigma t, no sigma f, and sigma t. So just the standard deviation in the frequency and in the time domain. And now we can apply that. And I would just, there's an additional parameter plot. Then you get an output plot with a spectral and temporal bandwidth or width and the number of cycles. So in our example, we had a constant temporal full width at half max of 250 milliseconds, which would be a constant spectral bandwidth of 3-point-something Hertz and a linearly increasing number of cycles per frequency. And if you put a data vector, so only vectors, no matrices, so no epoch data or so, you even get a time frequency, a very simple time frequency transform of the data. For that example only here, this is a synthetic data set from a very important publication, which is very useful for looking at time frequency decomposition algorithms. And you see that we now have indeed an STFT. So the temporal and spectral bandwidths are constant, and each slice, so a column, would be an FFT, and we just take an FFT, shift one sample, next FFT, that is short STF, short-term Fourier transform or Gabor transform. And of course, we also have different versions in previous papers. So again, also this Talon-Baudry and other communities, and also, of course, if you have guests from Osnabrück here, from Gruber and colleagues, they also typically use constant cycles. So that would be then a line here on the cycles. What would mean that the spectral bandwidth, so we have very high resolution at low frequencies and low spectral resolution at high frequencies, and vice versa. In the time domain, we have very bad temporal resolution at the low frequencies. So you see that going from the previous. So here we saw structure, and now the structure is completely gone. So we have very bad temporal resolution at low frequencies, but very good temporal resolution at high frequencies. And basically, in my opinion, this imbalance between very low and high frequencies in the temporal as well as in the frequency domain is extreme if keeping cycles constant for EEG and MEG data, and there are better alternatives. And again, that is not my suggestion. That was already suggested by others. I just implemented, I tried to implement an accessible way to actually use that. And in the paper by Mike Cohn, which it's at the end at the references, if you can download the data, and I just made now different versions with the time frequency decomposition, which is contained in the cycles calculator, but you can also do that with any other thing. So here you see basically the effects on the time frequency decomposition of EEG data. So here we have two versions of STFT. First with high temporal. So these boxes reflect the temporal and spectral full width at half max. So that would be the temporal full width at half max, and that would be the spectral. And you see immediately how that affects the results of your time frequency decomposition. So we have a very bad frequency, but very good temporal resolution. You see temporal structure here. And here we have the opposite. We have a very bad temporal, but very good spectral resolution. So we see very good spectral features here. And of course, we need to find a compromise. So that would be the constant cycles compromise we have in a lot of communities. So very good spectral resolution at low frequencies, and very good temporal resolution at high frequencies. So that would be the different full widths at half max. Just again, these boxes. In some traditions, so in particular the EEG lab community now, so SCCN and others, they use linear increase of cycles from low to high frequencies. Also there's Eric Rawls preprint who suggests or uses that. So it's basically a softer version of the constant cycles thing. So, but again, they try to balance resolution at high and low frequencies with less extreme than with constant cycles. I would personally, but that is just personal, it depends on application, so take that with a grain of salt. It's very specific. Something in between. So, for example, if we scale, that's now something we can do with the calculator, the full width at half max from 500 milliseconds at low frequencies to 200 at high frequencies, we get a pretty balanced picture across the full time frequency plane. Or very similar, it's just an example. We can, of course, we can do that temporally or frequency-wise. So here we would have a 2 Hertz frequency resolution at low frequencies and 6 Hertz, so slightly wider at high frequencies. And if you want, you also get the plots you had seen before. So the flat lines, that would be the STFT thingy. The yellow line would be the constant cycles line. And constant cycles, indeed, there's a linear increase of spectral bandwidth, full width at half max bandwidth, but not, and that might be very misleading, of temporal bandwidths. That's why I think this linear increase of cycles is suboptimal, but rather directly increase linearly your full width at half max in the time or in the frequency domain, which is basically the filter-related and intuitively accessible property. And now we could look at it in EEG lab, but I think that is I think it's sufficient if we look at that plots. So in EEG lab, the relevant function is pop new time f. And you typically at first add your frequency vector, either as a min and max frequency or as a frequency vector. So for example, 2:1:40, then you would have all frequencies from 2 to 40. And now the new part is this TF cycle calc button, where you get to that interface. First, you select your unit, and you have the same units I told you. So you have full width at half max in frequency, or so in hertz, or in temporal domain in seconds, or you can have 2 sigma t or sigma t or cycles. But that is, of course, only reasons those cycles they could directly enter in the old interface. So that is only useful if you want to recalculate papers or so with the GUI and do not want to use the command line interface. And then you can either add a single number here, then it's constant across the whole temporal or spectral, across all frequencies. So for temporal and spectral resolution, that would be then STFT. You could use 2 numbers. You could use 2 numbers even if you would have a frequency vector here. Then it's linearly spaced between the lowest and highest number with the number of frequencies. If you only have 2, then also frequencies will be spaced. Then you get it's fine. So that would be linear spacing, or you could have log spacing. What is in particular useful if you have log spaced frequency units, if you do not have a linear frequency vector. And there's a plot where you end up at the plots exactly the same output which I just showed you, and you can even collect different versions and check them one against the other. Good. So I hope there are still some questions. And we have 10 to 8, so perfect in time. So we have 10 minutes time for a specific and general discussion. And basically, first you get the slides of the third part, and there is on the GitHub page, there's also a wiki page explaining that in detail. And possibly I will make a manuscript out of it, but I'm not sure yet whether it's worth a separate manuscript, because it's just an implementation of ideas which were existing before.
So thank you very much. So if there are any more questions, please, take a moment to process all the information.
Yes, no, I have time, so there's no need to hurry.
I think I will take over for the slides now. People can think about it for a question. And if there are no more questions, I will just go over to the usual advertisement of the next Neuro Talk Evening. But if so, please feel free to unmute yourself and ask Mr. Widmann what you would like to know. Oh, I assume. Oh, there's one more question. So.
So thank you again for the wonderful presentation. It was really valuable, and for providing so many papers that I'll have a look at. And I'll also need a little time to comprehend the last bit. But it's probably not so much filter related, but I actually had a question about interpolation, and I did have to, I did have artifacts that are, for example, the signal breaking off, or like movement artifacts and stuff. And I had to use interpolation to save a signal that was actually otherwise good and didn't require much of filtering. I wanted to ask you, how much would is that a huge distortion? Do you generally recommend using interpolation, or should we just avoid it at all costs? And yeah, it's probably a stupid question, but
It's definitely not a stupid question, and it's basically also basically related to filtering. It depends. The interpolation there, it's a bit unspecific what kind of interpolation. So, for example, we all use spatial interpolation if some electrode or MEG sensor was not as expected.
and
And
yeah, Sorry for interrupting. It was something like that. It was, for example, the signal would be going really well, and at some point there would be like this large spike, and it would break off for like 2 or 3 points, and then it would continue. It would continue. So I assume that it was some electrode misplacement or movement or something like that.
And then again, it depends whether you, for example, in EEG, MEG, if you have a trial structure, I would not interpolate, but throw away a trial.
Right.
And if you have a long-term, basically a sleep data set, and you have movement artifacts there, you will, of course, need some kind of interpolation. But you might, that is basically also some kind of noise. So it depends. Filtering that kind of noise can be problematic, but it can also work quite well. It really depends. For example, we have also noise from MRI or noise from TDCS or other electric stimulation, which we can model and subtract, which is also in not spectral filtering, but also filtering, which would be better than interpolation. So they, if there is no other way to save the data, of course it's fine, but of course it's also in frequency-wise not necessarily optimal. So you cannot do a frequency analysis of interpolated signal easily. Because just you removed all that parts. So there is no really a general answer. There are very many specifics where the correct answer would depend on. Does that help?
Yeah,
Sorry.
that is really helpful. I'm also a beginner, so sometimes it's a bit confusing.
Yeah.
And there's a lot of information in internet, so yeah. But thank you
basically
again.
what we can typically do is what we regularly do is interpolating spatially. We just had a drop out of MEG sensor or EEG electrode. So we can do that for a whole data set. Or what we can, for example, do is if we have a broken temporal piece in a long-going recording, we can, if we have some additional information from additional sensors which are surrounding our sensor, we can interpolate that sensor only for a particular time. That would be something. So if we have any kind of information we can use for interpolation, that is helpful. So just a linear, just drawing a line between 2 points is, of course, the least optimal solution. And you have to be aware of possible side effects. But if there is not more supporting information, then of course you are at the point where you are.
Yeah. Thank you so much again. That was really valuable. And thanks again for the presentation.
Thanks for listening.
So, and I think considering the time,
sorry, was it too long? I'm sorry.
No, it's totally fine, but it's about 2 hours, and that's perfect. We met that perfectly. So thank you very, very much. I guess most of us said it, but I would like to say it again. And with that, we come to the end of this evening. The next Neuro Talk Evening, and also the last of 2025, is on the 4th of December by Dr. Neumann from the University of Würzburg. Sadly, she didn't reach out and gave us a deadline now, but we will make it official as soon as we know. So you can look that up on our website, and we also will announce that. If you would like to see more from Mr. Widmann's work, you can look up his homepage, his Scholar, also his many GitHub pages, and also his university page. And as always, if you want to see more from us or have a more detailed look at our projects and what is going on or what's coming up, you can always take a look at our website. And yeah, with that, thank you very, very much and have a great evening. See you again.